Hello everyone. So in this particular video we will go through overfitting, bias, variance, L1 and L2, regularization. So overfitting. Overfitting in machine learning occurs when a model learns the training data too well and starts to fit the noise or random fluctuations in the data rather than the underlying patterns. As a result, the model may perform well on the training data but poorly on the new unseen data. This can result in the model having high variance and low bias, meaning that it is too flexible and has learned the noise in the data instead of the underlying patterns. So first, now I'll explain what is bias in machine learning from a layman's point of view. So think of a machine learning model as a computer program that makes predictions about things like what items you might like to buy or who is likely to get a disease. A bias in a machine learning model means that it consistently makes wrong or unfair predictions about certain groups of people or things. For example, if a model has a bias against women, it might consistently predict that they won't be interested in a certain type of product, even though many women might actually like it. This is a problem because the model is making decisions that are not accurate or fair. Bias in machine learning can come from the data used to train the model, the design of the model itself, or the way it is being used. It is important to try to identify and fix biases in machine learning models to make sure they are making the right decisions. Okay, now technical term of bias. In machine learning, bias refers to a systematic error in the algorithm's predictions or estimations caused by underlying assumptions or sampling in the data used to train the model. A biased model may consistently over or underrepresent certain groups, leading to unequal and unfair outcomes such as discrimination or incorrect predictions. Bias in machine learning can also arise from the selection of features, the choice of algorithm, or the interpretation of results, among other factors. It is important to identify and address bias in machine learning to ensure that the models used are fair and accurate and do not reinforce existing inequalities or cause harm. Next, we'll see what is variance in machine learning from a layman's point of view. So think of a machine learning model as a chef who is trying to make a dish. Variance in machine learning model is like the chef trying different recipes for the same dish. Some recipes might work really well with the ingredients they have, but might not work well with other ingredients or in other kitchens. A model with a high variance is like a chef who uses a recipe that works well in their kitchen but is too specific and won't work well in other kitchens. A model with low variance is like a chef who uses a simple recipe that works well with the wide range of ingredients and in different kitchens. In machine learning, having a model with a right amount of variance is important because it helps the model make accurate predictions in a wide range of situations, not just for the specific data it was trained on. So, variance in machine learning from a technical perspective definition. Variance in machine learning refers to the amount of variability or spread in the predictions made by a model. In simpler terms, it measures the model's sensitivity to a small fluctuations in the training data. A model with high variance tends to overfit the training data, capturing noise or random fluctuations in the data instead of the underlying pattern, and may perform poorly on unseen or the test data. On the other hand, a model with low variance may have a simpler structure and may underfit the training data, resulting in poor performance on the training data and poor generalization to unseen data. Striking a balance between variance and a bias is crucial in machine learning, as both high variance and low bias can lead to poor performance. So this is the graph. So we want to have a model which has low bias and low variance, something of this sort. When we have low bias but high variance, so low bias and high variance, we will end up with overfitting model. And when we have high bias but low variance, so this will be a data over here. it is just focusing on a particular group. So this will be like underfitted model. And the last category is the worst, which is like all spread out, which is high bias and high variance. So that's why data is all spread out without being able to focus on what is required to be predicted. To fix high variance, collect more data, use regularization methods such as L1 and L2 regularization, feature selection and feature engineering, try different algorithms, ensemble multiple methods. And to fix high bias, collect more data, increase model complexity, example, add more hidden layers or nodes in a neural network, feature engineering to create new and relevant features, and try different algorithms, ensemble multiple models with different biases. Okay, overfitting can be caused by complex model. A complex model with many parameters can easily fit the noise in training data, leading to overfitting. Insufficient data. When the amount of training data is limited, the model is more likely to overfit as it is trying to learn both the underlying patterns and the noise in the data. Outliers. Outliers in the training data can have a significant impact on the model if not handled properly, leading to overfitting. And feature engineering. Over-engineered or unnecessary features can lead to overfitting as the model is trying to fit the noise in the data. Hyperparameter tuning. Choosing hyperparameters that are too high can result in a complex model that overfits the data. Okay, now we'll just we'll see what is a loss function. A loss function is a mathematical representation of the difference between the predicted output and the true label for a given input. It measures the error or discrepancy between the model's prediction and the actual output and is used to optimize the model's parameters during training. The goal is to minimize the loss so that the model can learn to make accurate predictions. And let's see some different types of loss functions. We have mean squared error, mean absolute error, binary cross entropy loss, categorical cross entropy loss, hinge loss, KL divergence loss, and cosine similarity loss. So next we'll see what is the model complexity. Okay, number of parameters. So what factors contribute to model complexity? So these are some of the factors. So number of parameters. The number of parameters in a model is a good indicator of its complexity. More parameters generally mean a more complex model with higher capacity to fit the data, but also risk of overfitting. Model depth. The depth of a model or a number of layers can also be an indicator of its complexity. Deeper models have higher capacity but also higher risk of overfitting. Model architecture. The complexity of a model can also depend on its architecture, such as the type of layers used and the number of neurons in each layer. Complex models such as deep neural networks can have millions of parameters and are more likely to overfit. Training time. The training time of a model can also indicate its complexity. More complex models generally take longer to train and may also require more computational resources. Okay, so now we have seen what is a loss function and what is a model complexity. So this is a graph. So x-axis we have model complexity. So it starts from 0 and it becomes more and more complex as we go towards the right. And same way we have loss function. So loss function starts from 0 and it keeps going up. So remember, the loss function should be as close possible to 0. So if it is closer to 0 or more towards bottom of this y-axis, the model is better. Loss function, high loss means not worse model, like, and less loss means better model. So it's from bad it goes down to good, and model complexity is just basically how complex your model is. So anything over here will be very less complex, and as we go towards right it becomes more and more complex. So we can see, right, the loss function is very high when we have model which is very plain simple model will have a very high, but as we go through like this, model complexity So we can train a lot, and this model complexity will keep going up, and the loss will keep going on. This is on the training data. So we are reducing the loss by increasing model highly complex. This is the training data. So now when we have the validation data, so we will see the loss first. It will go down, which is a good thing, and model is becoming complex. So we are reducing the loss. Model is improving. Model is becoming complex, and at this particular point, it has become, loss has reduced, but model complexity has come. But if we go more towards right, model complexity is keep going up, and like model complexity is going up, but the loss is also started to increase. So at this particular point, this is a sweet spot where the loss and model complexity is balanced, and this is the line wherein we say like anything left to this line is underfit model. Though this model is underfit, and anything towards the right, it's overfit, because overfit in the sense it has learned everything about training data so well that it is overfitting. But when we have the validation data with the test data, it will not be able to predict correctly. The loss will become higher because we will incur losses, and that's what we have to do. We have to get the right balance, and we have to come somewhere over here. And this line is called the balanced fit, optimal fit, and this will become more clear by this graph. So we have this green spots are for example, the training data, and we have created a model, but this model is very simple. It's just a straight line, so it is underfit because it's just predicting few points, and it is closer to some points but bit far off. So if we give it a new, like this is red is, for example, if we give it a new test sample data, so for example, if this x-axis is height and this one is weight, so based on height predict the weight. So it will predict weights, the weight should be somewhere over here, but it will predict here. So it has missed by a long margin this line from red to blue. So this one, for example, if you think this one is the actual or true value, and this one is the predicted, this is the line, and it is missing by a huge margin. So this will be calculated in the loss function. How much is the loss that we have incurred, and the higher the loss, the worse the model, remember. And next we have the underfit problem. So we have trained the model so much that it has learned all the training data perfectly. It has memorized every possible, and it has come up with a very complex polynomial, very high degree polynomial function. So but when we give it we give it a sample data, the prediction will be made. Blue is the prediction, it is very far off, and this is the actual value. So for height, the weight will be predicted as somewhere over here, and if we calculate the vertical line distance, it's very high. So it is actually performing even worse than underfit. So we have to come up with some line like this, which is a balanced fit, and which learns the training data, which generalize on the training data. So when we throw test data, for example, the vertical distance will be very less between test and predicted value, and this will be the balanced fit. Even if you throw some more data points, the loss function will be less. In this case, the loss is very high, and in this case also high, but this case will be balanced if you throw in a lot of test data points. So to prevent overfitting, some of the techniques are regularization, cross-validation, early stopping, simplifying the model, ensemble methods, dropout, data augmentation. Okay, now we'll see the last part, regularization. So regularization is a technique that adds a penalty term to the loss function to discourage the model from fitting the training data too closely. So it tries to penalize if the training data is to solve the overfitting issue. So if it is fitting the too closely, it will penalize, and that will reduce some of the weights. Common regularization techniques include L1 and L2 regularization, which add a penalty term proportional to the absolute or square value of the model parameters respectively. Regularization helps to prevent overfitting by encouraging the model to have smaller and more interpretable parameters. Okay, cross-validation is a technique that splits the data into several folds. So this is one of the techniques for preventing overfitting. So cross-validation is a technique that splits the data into several folds, training the model on some of the folds and evaluating its performance on the remaining folds. This provides a more accurate estimate of the model's performance on new data, as the model is evaluated on data that it has not seen during training. Next is early stopping. Early stopping is a technique that stops training the model when its performance on a validation set starts to decrease, indicating that overfitting has started to occur. By stopping training before overfitting becomes severe, early stopping helps to prevent the model from memorizing the noise in the training data. Simplifying the model. Simplifying the model, such as reducing the number of hidden layers in a neural network, can help prevent overfitting by reducing its complexity. Ensemble methods. Ensemble methods such as random forest and gradient boosting combine the predictions of several individual models to produce a more robust and accurate prediction. By combining the predictions of multiple models, ensemble methods help to prevent overfitting by reducing the variance of the model. Dropout. Dropout is a technique used in deep learning that randomly drops out some of the neurons during training. This helps to prevent overfitting by forcing the model to learn multiple independent representations of the data rather than relying on a small number of neurons. Data augmentation. Data augmentation is a technique that generates new training samples by transforming the original training data in various ways, such as rotating, flipping, and scaling. By increasing the size of training set, data augmentation helps to prevent overfitting by reducing the variance of the model. So now we'll see the last L1 and L2 regularization. So just this is the mathematical equation. So loss function we are calculating the loss original plus this one is the lambda, this one is the hyperparameter, and for all the weights, the coefficients, all the weights, so we are just summing absolute values. So this one is absolute. So if it is negative, it will be made positive. So we are just multiplying lambda with all the absolute value and adding it all. So loss original is the original loss function. Wi is the ith model parameter or the weight or the coefficient, and lambda is the hyperparameter that determines the strength of regularization. So we are adding a penalty, as we can see. So this, when you add this penalty, the loss function has to go down, because the model the goal of the model is to reduce the loss function. So to reduce the loss function, it will work towards reducing the weights, or sometimes it will even remove some of the features which don't add any value. So it will automatically learn all those relationships between all the features, with their weights and all, and it will keep adjusting so that this loss function is reduced. And this one is like this one has an absolute value. So x will remain if it is 0 or more, and if it is minus, it will be just turned if it is less than 0, it will be minus x. I mean, just the positive value it will take. So if it is minus 5, it will be taken as 5 only. So L1 regularization, also known as lasso regularization, is a method used in machine learning to prevent overfitting. It adds a penalty term to the cost function that is proportional to the absolute value of the coefficients of the model. This helps to shrink the coefficients of less important features to 0, effectively removing them from the model. This results in a model with fewer features, which can be useful in cases where the number of features is large and there is a risk of overfitting. The regularization term is added to the cost function in the form of like this L1 regularization, which we have already seen, and we sum all the weights, and then we put all the weights and and multiply it by the lambda parameter. This one is like hyperparameter, where lambda is the regularization parameter, also known as regularization parameter, a scalar value, and the W is the weight of the features. The regularization parameter controls the strength of the regularization with a larger value resulting in a stronger regularization. So larger values means stronger penalty. So when you have stronger penalty, the loss function will go up, and the model will try to reduce some of the weights or a lot of weights, and sometimes it will even remove the complete weights, and some other features it will bring it close to zero. It is important to note that L1 regularization can lead to sparse solution. Sparse solution in the sense, as I mentioned, some of the features will be removed, and that's why it will become sparse, because there will be less and less weights and features, meaning that many of the feature weights will be exactly zero here. This can be useful in feature selection, but it can also lead to a model that is less interpretable, because we have removed essentially we have removed some of the feature weights. If feature weights become zero, then feature itself will have no impact. In addition, L1 regularization is not always the best choice, as it can be sensitive to the scale of the input features, and it may not work well when the number of features is large compared to the number of samples. Okay, next is L2 regularization. So this is the L2 regularization, how it's called, calculated. So we have loss original. So this is a new loss function, and we are adding this penalty, this regularization parameter lambda hyperparameter, and what we are doing, we are taking all the weights and we are doing a square of that and summing and multiplying it with lambda. So loss original, the original loss function, the ith model parameter weight I, so weight 1, 2, 3, or the coefficient also known, and lambda hyperparameter that determines the strength of regularization. So let's see what is L2 regularization. L2 regularization, also known as ridge regularization, is a method used in machine learning to prevent overfitting. It adds a penalty term to the cost function that is proportional to the square of the magnitude of the coefficients of the model. This helps to shrink the coefficients of less important features towards zero. So just remember it, less important features towards zero, effectively reducing their impact on the model. The regularization term is added to the cost function in the form of like this, which we have already seen, where lambda, so cost function, so again this is also a penalty, and this will make sure the loss function should be reduced, and that's why the weights and features multiplication and addition should be reduced, the overall loss function. So where lambda is the regularization parameter, the scalar value, and W is the weight of the features. The regularization parameter controls the strength of the regularization with a larger value resulting in a stronger regularization. L2 regularization will not force the coefficient to be exactly zero. So this is the difference. It will not force the coefficients to be exactly zero, but rather it will drive them to be small. This can be useful in cases where the model has too many features and is at risk of overfitting. L2 regularization tends to work well when the number of features is large and it is not sensitive to the scale of the input features. It is also important to note that L2 regularization can be used with other types of models such as neural network. It is known as weight decay, where the L2 regularization term is added to the weights gradient during backpropagation update. It is also common to use a combination of L1 and L2 regularization, which is called as elastic net regularization. This can balance out the strengths and weaknesses of both L1 and L2 regularization, resulting in a more robust model. So the difference, we'll just remember, both are exactly same, except this the lambda function is the summation with the absolute value, but herein we have the lambda multiplied by the square of the weights, and this one is absolute weights. So just last point, differences between L1 and L2. Left hand side is L1, right will be L2. So adds a penalty term to the cost function that is proportional to the absolute value of the coefficients, adds a penalty term to the cost function that is proportional to the square of the magnitude of the coefficients. This has the effect of shrinking the coefficients of less important features to 0, effectively removing them from the model. This has the effect of shrinking the coefficients of less important features towards 0, reducing their impact on the model, not removing, reducing. This results in a model with fewer features and is useful in cases where the number of features is large and there is a risk of overfitting. L2 regularization will not force the coefficient to be exactly 0, but rather it will drive them to be small. It can perform feature selection because it will remove some of the features. That's why it can perform feature selection and produce sparse models with less features. That's why sparse means less number of features. Produce sparse models where many of the feature weights are exactly 0. So if feature weights are 0 and feature is multiplied by weights, that feature also becomes 0. This can be useful in cases where the model has too many features and is at risk of overfitting. Useful for feature selection, and L2 regularization tends to work well when the number of features is large and it is not sensitive to the scale of the input features. Scale means the magnitude, like what is the range. So range can be start from 1, 10, 100, millions, or whatever is that number. So scale, if the scale is huge, and it is useful for preventing overfitting. And that's all. Thanks for watching. Bye.